So we said that we see cats, trees, and different things in the image, but what would machines see when we first take the camera? I just literally sound. Yeah. Is it better? Okay. So I think Azad covered this in the first lecture about how from 3D objects we get the 2D images in the camera, right? In that imaging with the pinhole camera model, the images gets projected in the plane. That's what and then we have intensity values, RGB or just grayscale. And what are okay, I think I should first ask, well, what are the components or things that can impact the image values, these numbers that we see over here? So what does it depend on when we use a camera? Let's say I'm taking a camera and taking a picture here. So what we will get is a certain number on an image, right? So what does it depend on? First, the object. So given the object is the same, so what would it depend on then? Yeah. Distance, light. So distance, it gives a scale. So, and yeah, mostly it's light, camera, sensor, and the object itself, and the way it reflects, right? So that's the three major components we have where the image formation depends on the kind of sensors you're using, and usually in the normal camera sensor we have these three R, G, and B wavelengths that gets absorbed. And depending on the illumination, the intensity values can change. And this also makes it difficult when we try to extract features that we will see later on briefly on trying to build algorithms, because in the 80s, 90s, and early 2000s, lots of people use lots of ways of extracting features from these images, like edges or these different things, and try to describe the image based on that. But since this exactly the same object can have so many different values of images depending on whether it's on sunny conditions or darker conditions, shadows, clouds, all those stuffs, right? So now it's so obvious for us, the images, okay, we can say what's in the images, but now if we want to make that kind of capabilities in the computer, so one of the first things to do is to represent the images as objects or structures, and we can, I think you already know this, but the images is it's a function of a special location, right? So in the 2D matrix, when we show it as a 2D matrix, so there's a location, and we have an intensity value. So it can be a scalar function. So it's a function with the input variable size in 2-dimensional. So the x and y coordinate, right? And what we get is intensity. If it's one single value, it's a scalar function, but it can also be vector valued function in usually RGB, 3 channels, or there can be many other kind of spectral images where you can have even more number of channels. And in 3D images, which we will see next week with medical images or with 3D point clouds, and you can have not just X, Y in an imaging plane, but the whole 3D space where we define image values, intensity values. So that's this is a function where the input variable, the spatial locations, is in 3D. We can still have scalar or again vector functions of these 3-dimensional variables here. Now, so that's let's say the first step. So now we have a structure. We know it's a function of spatial locations. We defined image in some very, very basic mathematical way, right? So in our head, we know there's a certain locations, and we have values on those locations, which is like a function image. Then the question starts coming. Okay, we can system. So that means I have images are like objects now. One image is one object. Then what is it closer to? So we see here 3 images. What do you think? Which images are closer here, or similar, if I say? first and second, yeah. So we say they are similar because we have certain notion of this similarity. When I asked which are similar, you could have asked me, but what do you mean by similar, right? But then it comes, even before that, you instinctively say the first two are similar because this notion of similarity is ingrained in our learning and the model that we have made of this world. So how do you think, okay, so now we have represented images as functions or objects, so we know that these images can be defined as I of special locations. So now if we want to compute the similarities in mathematically or in computer, what could we do now? Any ideas? Sorry? Distance? So how would we compute distance? Formula. So so the notion of distance. So if we go back to our high school and in the vectors, so there are two vectors and we can compute distances in Euclidean space, right? So in the first day we talked about this three-dimensional Euclidean space, briefly vector space, those stuffs. So if we have two vectors or two points in this space, so we have a notion of distance, what's a Euclidean distance, right? So the distance between these 2 points, how do we compute it? L2 norm, or it's, if we say it in a very basic way, this is defined with x1, x2, and x3 as three components of a point, and then another point as y1, y2, and y3, we know how to compute, right? So it's a sum of squared differences, x1 minus x2. But even before going that, what are the assumptions we already made here? We already made an assumption that these 2 points lie on a certain kind of space. And there is this notion of in this space, distance means certain things, right? So how do we do that for this image then here? So you said we can compute this. So how do we represent this image as a point? In which space? Yeah?
Image can be taken as a single vector, but
Mm-hmm.
it could be very high dimensional, so distance might not have
Mm-hmm.
much of a meaning because of the dimensionality.
Okay, yeah, that's okay. So what he said is we could take the image as a vector. So this is a vector operation of a matrix. So you can think of that A as a very tiny image, small image with certain values, because it's so we have a two-dimensional x and y coordinates, and you have scalar values there, right? So it's a grayscale image. And now we can vectorize it. So the first rows can be written as the 2, 3, 4, and then so 2, 3, 4, the first row comes, and then you can stack all the rows. So as soon as we did that, so that's what he told, that we can take the distance. So we have all these mathematical formulations which we can use to compute distances. Because this is now a vector in which dimension? Yeah, from behind. Which dimension is it now? 6, right? So 1, 2, 3, 4, 5, 6. So this we are representing. So it's just a matter of representation, and it's all about how do we represent these images. That's what we will be learning next week also. Whether we state how we want to represent image, or we want some deep networks or something else to learn on its own what's the best way to represent. But now we're starting at a very, very fundamental level, saying, okay, I have an image. I want to represent it as a point in a 3D Euclid. So this is not 3D. So it's a 6-dimensional space as a point over there. This is how we define this. And we have all this linear algebra and Euclidean space geometry to define a distance over there. Yeah? So so this is what we explained. Can you think of other distances? I think some of those distances you learned this morning or yesterday when they talked about L1 norm, L2 norm, so norms, right? So you could take, let's go back to the images. So you could also have said, let's just take the difference between the images, subtract these images as a matrix, subtraction, and then take the absolute values, because it can be negative. We just want to know how far each pixel is here, and then sum it, right? So that's still a distance once you take the absolute values. So that's what is L1. Well, you could do that, right? So you're no more squaring the distance and then you're taking this. This is another distance. So these different things have different properties. These L1 norms, L2 norms, and there are other norms in between, or even L0 norms, these things, right? So, but we won't go into that detail because we just want to see how we can formalize the real world problem into structures here and see the notion of these space, distances, representation, these kind of things you will come across when you go into more complicated stuffs. For now, very basic, just two distances. We could use that. Okay, let's see what happens. I think if you use this particular image, if you use sum of square difference, the kittens are farther apart than the clouds, because perhaps this blue sky and the number of blue skies, perhaps it's closer, or it can happen, right? So what does this show? Sorry? I think we should have a mic so that I can hear them. Taman, mic here. Oh, okay, it's here. Yeah.
It's okay.
So someone was saying, yeah.
So I think when the computer sees those images, they just see it as a pixel. Mm-hmm. When we see it, we already have an idea. Like say, I'm really looking at the what is it, cat? Mm-hmm. I'm really looking at the cat and not really looking at the background and everything. But when computer sees it, they're looking at overall picture as a pixel.
Yeah. So that's when you look into papers, they say attention model, because we have this attention model. We are attentive to certain parts of the image. But even to reach that level, perhaps we have these structures in our brain, or the ways with which we extract features, perhaps. We're not looking at mere number of these values as numbers which are in our rods and cones cells, right? Because in our rods and cone cells in the eye, we sense these colors and brightnesses. And in the new networks, which perhaps tomorrow Suzanne and Pascal, they will talk about those stuff, so in neuroscience, how these things get processed. So just based on this, a normal distance, what Bishesh was also telling earlier, that this distance is not suitable. And this keeps on recurring in various forms in computer vision and actually in many other topics, right? What distance is good and what representation? So the key words here is the representation. The representing images as a points in this high dimensional space is perhaps not a good idea, or we see that here it's definitely not a good idea. That's one key notion we need to take care of. So when people talk about this million-dimensional image, dimensional space, there's nothing to be scared of. It's just, this is a huge, so if, I don't know how big this image is, or if it's just if we imagine it's 600 cross, I think I have that somewhere. It can be a huge dimensional image, dimensional point, right? And so we won't go into what manifold is and those stuffs, but you might come across these things. Where does this data lie? And these things will, perhaps we might talk about that next week. So the distance, representation, these are the things we need to get intuition or try to find ways to do that. I'm going really slowly because I think these are fundamental notions. Once you really internalize this, it's computations, you can just do that, and everything hinges on knowing these things really and building intuition on this, okay? So, yeah, as I was saying, so this is this dimensional space, so nothing to be scared of. Just you vectorize that, a matrix, and then you have this number of computed components. It's just a one point in that space. But what will happen, which we won't be able to go into detail today, is depending on these dimensionality of these spaces, the properties, these many things have really interesting behavior about points, about clustering, and how you can go like I think when you have these higher spaces, there's lots of empty spaces in big dimensional spaces. You can have some data point really far apart, because this way this space grows. So these sorts of notions we will need to build on later on. So the question is, so now, okay, brain is doing something more, right? So it is representing it something else inside. So can we do that? Can we extract from these huge, because there's lots of redundant information here too. So this sky looks similar. They have neighborhood structure of this spatial relationship. We know skies, similar things will lie around similar areas. So there's lots of assumptions we can make about our world. And based on that, can we compress or can we reduce this information into something that is more suitable? So that's the question. Any ideas? What could we do here? And try to represent it with a reduced vector. So imagine 2400,000 dimensional image. We know how image can be that dimensional, right? It's just stacking the rows as columns and making it a vector, which is a one point in that dimension space. And with PCA, with the method that we will show, you can reduce that to, could be, let's say, 150 dimensional vector. And it's one vector, now it's in another space. So it's a reduced, this is Euclidean space, where this reduced vector of, let's say, 150 size vector is representing a point, and this point is again still an image, but its representation is different now. And then we can use this to do this classification or separation, those sorts of things. And the other approach, which was predominant in the, let's say, until 2010, 2011, until the arrival of deep learning, lots of hand-engineered features about, and this gets also motivated by how humans, what was the famous Mars 3 levels of vision, about how we represent images inside the brain at different levels of hierarchy with edges, these kind of features, certain kind of shapes, and then go into higher level, higher contextual level slowly. So with these, people have developed lots of methods, so there's a huge amount of literature. I'm not going to make you bored with those things, but I'm just giving few examples that will also help you build few more intuition in the convolutional neural network next week when we talk about that. So we have an image. I think this might be around Pashupati. We cannot see properly the edges, I think, because it's too bright. Can you see some faint images here? On the screen, does it come better? Okay, so you're lucky then. Okay. So that's one way of extracting edges. This is the result. So can you guess how we could come up, how can we extract edges from images? Anyone? Difference? Yeah? Pixel value, sorry? Changes drastically. So how do we capture that mathematically? Because we need to implement something. Derivatives, gradients, right? Because we know derivatives are these mathematical structures with which we try to study the rate of change, right? And we know edges means there's some changes in the intensity pixel. So that's how okay, why not use derivative? So we know derivative, and this is the tool we want to use. So that's one way of coming up with these ideas, right? And similarly, there are other things we can do. Is Hoff transform, quite well-known transform, where you can detect lines on images. You can detect planes in 3D images, right? And very simple thing of just thresholding. So you have intensity values, and you say, okay, if it's higher than, let's say, 50, if the value is greater than 50, I make it 1. If it's less than 50, I make it 0. Doing as simple as like that, you can get some certain kind of features, let's say, because it's now binary, right? It's no more, it's 0 to 55. If the values were 0 to 55, now you reduced it, the range of the intensity value, you reduced it to binary. And these are the tools, and then slightly more involved kind of features this is Sift, Scale-Invariant Feature Transform. So scale here means taking from where you take the images and how big the image is. And invariance means no matter whether you take an image of an object from very close by, so that huge, or you go really far away and it's smaller, you still want to detect these key features. In this case, these different particular parts of this building. And to be able to do that, it's not that simple. Well, if you know, once you know that, oh, this is a simple algorithm, but to come up with these kind of things from your own head, you need these kind of tools. So I think Azad will briefly talk about this later on, right? About Sift. All right. And there's Surf, there are lots of corner detectors, Harris corner detectors, and so many other local binary patterns. There's a huge number, but you can read them, and it won't be difficult. But what's important is this notion of these features get extracted at certain level. And when you do convolutional neural network, these things can be useful also to have it in your mind. So before we see the edge detection, which people said we can do differentiation. So how do you do this differentiation in images then? So because you said we can do gradients, we can take the gradients. So now we need to implement that. So what kind of tools we have to do that? Because if I ask you if I give you y is equal to x square, and then ask you to do derivative by pen and paper, it's quite easy. We know how to do derivative. But now I'm giving you an image, and you need to do that in a discrete way, right? Because it's no more continuous images, and it's a two-dimensional object with the x and y. So convolution. So that's what we see here, the linear filters, correlation, the convolution. So I think we will do a brief exercise here, because a lot of people, I think, they enjoyed writing there in the board. First, so the notion of convolution is it's also applying a certain kind of filter or a kernel. So sometimes you hear people saying kernel, mask, filter. What it usually means is you have this big image over here, right? And you want to apply something over this image, and you want to extract some feature from that. And in our case, it was edges earlier, right? So we want to extract edges from the images by applying something here. And we also know that some of you already said that for extracting edges, because there's a big changes in the image intensities, the gradients or derivatives will be able to extract this. So this is also already in our head. So we just need to put these dots together now to be able to extract this. And the tool we have is a convolution tool here, and where we want to compute the new image by multiplying. You can think of this as multiplying this pixel here. So if you, I don't know if let me see if, yeah, okay. So imagine this filter here is overlapped at this location, and you want to compute the value of the output at this green location now from the image. So you multiply, so the pixel-wise multiplication of wherever you are getting overlapped, ij, and then you sum it over the 2D, right? So and there are tricky places in the boundaries. What do we do? We will come back to that later. Let's do that. Can someone do, it's there already, but still I think it's worth doing it on the board if anyone wants to. Can someone help me do that in the board? No one? Everyone is bored? Or is it too easy? Yeah? Too easy for everyone? Okay. Yeah, I think it's too easy. Nobody's bothered to come in the front. Can someone explain then? Okay, at least. Someone doesn't need to go to the board, but can someone explain it here with the mic? Otherwise, I'll have to randomly call a name. Does everyone know what's being done here? Because this is what all convolutional network, that's all convolution you will be doing in deep learning, at least in the imaging. Well, not everything is done that way, but a lot of this is done. And you need to understand this convolution very clearly. Okay, what he said is PCA can remove correlated features. So correlation, so that's another. So this, we talked about covariances, variances, right? So this is, again, it's really about building the priors, the knowledge. You know, in the first lecture when we talked about the three key features, or three key steps in AI, data, right? And then we had this learning and knowledge. So knowledge, we get in a lot of stuff from knowledge we have. And what he told here there about correlation means this is about knowledge we have about our world that we learned starting from when we were babies, right? So we can use this knowledge to do something about this data. And then we want to represent it in a low-dimensional space in an efficient way. So that's what PCA will do. And before we go into that, I'll briefly recap in 2 slides what Azad mentioned in the first lecture about eigenvectors. I think you remember this image, right? That's what he showed in the first lecture. And again, this very basic notion of matrix is just acting on the vector to create something. So it's just linear mapping. You map an input vector, which is x, and you get something that is b. I mean, we repeated it thousands of times. And generally, the output, the input x and b, can be in a different direction. But then there are cases where you get this in the same direction when you scale the input image just by a scalar. And this is what eigenvector is, right? So you have matrix, and those vectors which, when it acts on those such vectors that it's just scaling it up, scaling the vector, that's what gives you these eigenvectors and eigenvalues. So that's what we covered last time. So with this reminder, I think I'll go through the code of PCA, and then we will just quickly look. Try to represent it with a reduced vector. So imagine 2400,000 dimensional image. We know how image can be that dimensional, right? It's just stacking the rows as columns and making it a vector, which is a 1 point in that dimension space. And with PCA, with the method that we will show, you can reduce that to, could be, let's say, 150 dimensional vector. And it's one vector, now it's in another space. So it's a reduced, this is Euclidean space, where this reduced vector of, let's say, 150 size vector is representing a point, and this point is again still an image, but its representation is different now. And then we can use this to do this classification or separation, those sorts of things. And the other approach, which was predominant in the, let's say, until 2010, 2011, until the arrival of deep learning, lots of hand-engineered features about, and this gets also motivated by how humans, what with the famous Mars 3 levels of vision, about how we represent images inside the brain at different levels of hierarchy with edges, these kind of features, certain kind of shapes, and then go into higher level, higher contextual level slowly. So with these, people have developed lots of methods, so there's a huge amount of literature. I'm not going to make you bored with those things, but I'm just giving few examples that will also help you build few more intuition in the convolutional neural network next week when we talk about that. So we have an image. I think this might be around Pashupati. We cannot see properly the edges, I think, because it's too bright. Can you see some faint images here? On the screen, does it come better? Okay, so you're lucky then. Okay. So that's one way of extracting edges. This is the result. So can you guess how we could come up, how can we extract edges from images? Anyone? Difference? Yeah? Pixel value, sorry? Changes drastically. So how do we capture that mathematically? Because we need to implement something. Derivatives, gradients, right? Because we know derivatives are these mathematical structures with which we try to study the rate of change, right? And we know edges means there's some changes in the intensity pixel. So that's how we, okay, why not use derivative? So we know derivative and this is the tool we want to use. So that's one way of coming up with these ideas, right? And similarly, there are other things we can do is Hoff transform, quite well-known transform, where you can detect lines on images. You can detect planes in 3D images, right? And very simple thing of just thresholding. So you have intensity values, and you say, okay, if it's higher than, let's say, 50, if the value is greater than 50, I make it 1. If it's less than 50, I make it 0. Doing as simple as like that, you can get some certain kind of features, let's say, because it's now binary, right? It's no more, it's 0 to 55. If the values were 0 to 55, now you reduced it, the range of the intensity value, you reduced it to binary. And these are the tools, and then slightly more involved kind of features. This is Sift, Scale-Invariant Feature Transform. So scale here means taking from where you take the images and how big the image is. And invariance means no matter whether you take an image of an object from very close by, so that hues, or you go really far away and it's smaller, you still want to detect these key features. In this case, there's different particular parts of this building. And to be able to do that, it's not that simple. Well, if you know, once you know that, this is a simple algorithm, but to come up with these kind of things from your own head, you need these kind of tools. So I think Azad will briefly talk about this later on, right? About Sift. All right. And there's Surf, there are lots of corner detectors, Harris corner detectors, and so many other local binary patterns. There's a huge number, but you can read them, and it won't be difficult. But what's important is this notion of these features get extracted at certain level. And when you do convolutional neural network, these things can be useful also to have it in your mind. So before we see the edge detection, which people said we can do differentiation. So how do you do this differentiation in images then? So because you said we can do gradients, we can take the gradients. So now we need to implement that. So what kind of tools we have to do that? Because if I ask you if I give you y is equal to x square, and then ask you to do derivative by pen and paper, it's quite easy. We know how to do derivative. But now I'm giving you an image, and you need to do that in a discrete way, right? Because it's no more continuous images, and it's a two-dimensional object with the x and y. So convolution. So that's what we see here, the linear filters, correlation, convolution. So I think we will do a brief exercise here, because a lot of people, I think, they enjoyed writing there in the board. First, so the notion of convolution is it's also applying a certain kind of filter or a kernel. So sometimes you hear people saying kernel, mask, filter. What it usually means is you have this big image over here, right? And you want to apply something over this image, and you want to extract some feature from that. And in our case, it was edges earlier, right? So we want to extract edges from the images by applying something here. And we also know that some of you already said that for extracting edges, because there's a big changes in the image intensities, the gradients or derivatives will be able to extract this. So this is also already in our head. So we just need to put these dots together now to be able to extract this. And the tool we have is a convolution tool here, and where we want to compute the new image by multiplying. You can think of this as multiplying this pixel here So if you, I don't know if let me see if, yeah, okay. So imagine this filter here is overlapped at this location, and you want to compute the value of the output at this green location now from the image. So you multiply, so the pixel-wise multiplication of wherever you are getting overlapped, ij, and then you sum it over the 2D, right? So let's, and there are tricky places in the boundaries what we do. We will come back to that later. Let's do that. Can someone do, I mean, it's there already, but still I think it's worth doing it on the board if anyone wants to. Can someone help me do that in the board? No one? Everyone is bored? Or is it too easy? Yeah? Too easy for everyone? Okay. Yeah, I think it's too easy. Nobody's bothered to come in the front. Can someone explain then? Okay, at least. Someone doesn't need to go to the board, but can someone explain it here with the mic?
We have an image which is a matrix of a intensity of the pixel values, and we have a filter with a size, suppose k by k. And in convolution, we basically overlay the filter from the start and multiply the weights with the corresponding intensity value. Suppose this is 1, 2, 3, 4, 5, 6, 7, 8, and 9. Then at first, we'll overlay this 3 by 3 matrix over here and multiply the intensity by the overlaying value, like 1 plus this intensity, 2 plus this, 3 plus this, 3 into this, and correspondingly, and we sum it all these values up, and here is the value 1 by 9, and the overall sum is multiplied by this, and we slide this window with a stride. There is a value called stride, and we perform for every individual central pixel. Suppose we overlay this over here 3 by 3, and in the result image, the pixel under the central pixel of the kernel is replaced by the result obtained from this convolution, like as shown in that figure.
So it's like, so here, if it's 1, 1, 1, this kernel, and if you are multiplying each individual pixel here, so how many pixels do you have in this filter? 9, right? And then you have this, so you're multiplying each pixel by 1, and then you add it. Now, if you divide by 9, what are you getting? Yeah. So averaging the pixel out, because you have a question?
Why is this matrix 1, 1, 1? Is it on purpose or is it?
So this is, so his question is, why is this matrix here 1, 1, 1, all 1? Is it on purpose, or is it something that we have to do? And then, so I think the two questions have an answer. So who was the next one? Who said why 1 over 9? Yeah. So we have one question asking why is there 1 over 9, and the other question asking why is it 1, 1, 1. So these are choices we've made, right? And these choices has a certain physical meaning. And what's the meaning here is we multiply a number, each number here. So we are multiplying each of these number by 1, adding them, because that's what convolution is. Now we are dividing it by, what is 9? 9 is the total number of these individual numbers we are adding. So what does it give when you add and divide it by the total number? Average, right? So what we are doing here is we are averaging the pixel in this neighborhood and replacing the central value by that average. So what it does is it smoothens or blurs the image more. But you don't, I mean, it's one, so we will see later on, for doing the edge abstraction, we need to do something else. And when we go into deep learning, what deep learning tries to do is it says, okay, don't tell me what I need to put here. I will find it on my own. Just tell me where I should go. That's, if you go down, I really have to explain in one, 2 sentence, that's it. That's exactly what it's doing, nothing else.
Also, why 3 by 3 matrix?
So why 3 by 3? That's again another good question. Now I think it's getting more interesting now. So why 3 plus 3? It's a design choice, one answer. But why a designer is choosing that? So that the 10, well, okay, but if we could have, let's say we were computing at this location, we could have 5 or 7 sized also instead of 3, right? And the center won't change at in that case. Okay, but why 3, 5, 7? So this is also, this will go into, when we learn deep learning, we will talk about receptive fields in the images, and it's, why is it important? But in this case, it's about, so, yeah,
You want to answer?
okay.
I think we'll obtain a center in the middle if we take odd and odd. So, like,
So odd and even, okay, yeah, it's
sorry,
we want
even
the
and
centered
even.
in the middle, that's why odd, that's
Yeah.
fine. But the question is why 3 and not 5 or 7?
Yeah, like there are other filters as well, like a Gaussian filter, 5 by 5. So they are also famous for approximations. So like it's purpose dependent, like you
Okay,
said.
purpose dependent. So what kind of purposes
So for
would
normalization,
make us choose 3 instead of 5? Or, so can you give some examples? Like what is changing when we say, when we increase the size? So okay, let's get back to this. What if we used, instead of 3 cross 3 filter, if we used 5 cross 5 or 7 or 9 cross 9, even bigger, what will it do? Sorry, less accurate. But what's the definition of accuracy for you in this case? Because when you say accurate, less or more accurate means you are targeting to achieve something. You're trying to predict something, or you're trying to get something, and not being able to be close to that means you're not so accurate. But what are you trying to achieve here to say that you are less accurate? In a hierarchical, yeah. Yeah. Yeah, so that's one way of saying if you go to the hierarchical. The other way of saying is what's happening is, again, it goes back to, I always like to emphasize on what's the physical assumptions we are making. What are we trying to do over here is we want to erase out the pixel, blur this thing. I might have an example, let me see. Not here, okay. So, okay, this one here. So we are blurring with this filter. So okay, this example. So the result of applying this 3 cross 3 over here is this. So what happens if we use a bigger size? Is the question. So the assumption here is what we are doing is we want to update the pixel values, right, at a particular location by taking in average of. So what does average do? Let's see over here. So if we have, let's say, heights of people here in our classroom, right? So the heights could be someone is tall, small, and there is certain variation. And if I start taking an average of, let's say, every 5 persons, I start taking an average. So what will happen? So there will be a certain average, then another average. So what will happen to the variation in the height? So it decreases. So what if I take the whole, let's say I split just into 2 halves and then take the average. So it starts getting smaller. One, you'll start having a lot less numbers. So just 2 numbers. If you split the whole group into 2 and take the average, so it's just 2 numbers now, 2 averages. That's an extreme case, let's say you're increasing the size. And the other thing is you're getting smoother, right? So because you are taking this information from a lot of things. And it's similar here. If you go bigger and bigger size, the result can be you get smaller and smaller images. Well, if you don't do padding, that's a different. Another is you are smoothing it much more. You're taking you're taking a lot of information and reducing the variation. So that's so that's the choice you want to make when you. So if you are, it depends on your application. What do you want to do? So to answer that is whether you want to smoothen it more, whether you want to use the information from a large area or in the neighborhood, or not of the image. No, so we will detect edges later. Right now, we're just using this before detecting edges, explaining the convolution operation here, that you can do this and then you shift it, and also the notion that you can, depending by using a certain values in this filter, choosing a certain kind of values, you're doing something. You're acting on an image to produce something else. So in this case, what I think by mistake I already gave you the answer. But what would be the result applying this? Yeah, same, because it's 0 everywhere else, and in the center it's 1, right? So choosing. So you see, the depending on what we put in the convolutional or the kernel filter, the output can be different. So here it's getting smoothed. And so this is, and I was just explaining how we can do that and what are the things we need to take care of, size and what we want to put. And the other one is the padding, which is here. So what will we do when we are at the edge? Because there is no more values here, right, to multiply. So what shall we do here? Padding. So padding means adding some values. So increasing the size of the image and filling it with certain values. So what kind of values to put over there? Okay, zeros. Same as image edge. Same as image edge. Based on the neighborhood values, yeah. So whenever you're saying this, there are certain assumptions you're doing, or depending on what you want to do after, you are making it easier for that, whatever the follow-up method is after that. And these also have an impact. So I think yesterday or day before yesterday, someone asked me in the lab, someone was working on multispectral, so is working on multispectral imaging, doing deep learning to do segmentation of different cars or roads and these different objects. And there they needed to do padding. And what they chose was putting the value here, copying the value from this edge on the other edge. So it's like mirroring the. Are you aware of this kind of padding? Yeah. So it's like you're folding this paper so that this edge joins this edge. So this, and then perhaps in their application it might not have been suitable, because if you look onto, because it gives you almost unrealistic images in right, because this is an object, or let's go to this image here. Where is the, yeah. So what that means is I'm joining this part of the image with this one. But physically, this is very unlikely to happen. Because when we take the camera images, normal images, what we will see is if we slightly change the camera location and took the picture, we might have seen something that is here, or the cropped version only up to this point, right? So maybe in that scenario, it might be better to do copying the same value, or just putting zeros can also work. It depends on also the image problem and how, I mean, especially if you're doing convolutional neural networks, it might not matter much. It might just learn that, right? But this mirroring can be useful in certain transforms. So people might have done Fourier transforms and those kind of signal processing. And so in those cases, there are certain algorithms that can benefit from this padding, just making it easy. But for mostly in convolutional neural networks, which you will be doing later on, I think either padding zeros or copying the same values might be more useful. Or any other methods people have used, because I might be unaware of some interesting methods. Padding. No? Okay. So now we go into, so this is again same correlation can also be seen as convolution with the negative values. I think we can skip this for now because it's, so now we go into edges, the original question, right? So some of you already said it's a sharp variation in images. So if we look at the gray values at this line in the image, so it has a certain value, well, and then it picks up and then goes again flat. So we need to extract, we need to identify this sharp change. And we know, we already discussed that the derivatives can do that, right? And so this is where convolution comes in. And how do we do that? So if you see earlier these, so the definition of derivative, at the limit we know that it's a small change in the x, and we look at the change in the corresponding change in the function value, and divide it with this small change, right? So, but we need this in a discrete form, and in discrete form, we can approximate it with this convolutional kernel. So this is in 1D, right? Is everyone clear with this, or perhaps someone can help us on the board how this is same as this to show it in a 1D? Anyone? Is it obvious for everyone, or we need to do this on board? Good, everyone? Easy, good, or difficult? Okay, I wait until I get the response. Yeah? In the middle, you mean why are we not taking the one in the middle?
Yes.
So I think if you can come here and try doing it, it might make it easy for you to see. So it's I mean, if you want to compute the value here in the middle, so there are different ways you can take derivatives or approximate the derivatives in discrete form. So are you aware of forward difference, backward difference, central difference, those sorts of stuffs? Yeah? No? Okay, I mean, yeah, you could do the derivatives by taking the, so if you have these three values, or so if you subtract the value from, so one, I can't use this Mac. No, it's okay. I think it will take two. We can get back later, I think, because yeah, I will have to show you in the paper. So now we can use this edge detectors where you're subtracting. So the, yeah?
I think it's also because of
Marker. Okay, yeah, we can carry on, and if the markers work, we can get back to it later on. The images. So I showed the vertical, horizontal, yeah? Sorry? Yeah, we have those there. Yeah, it's fine, okay. But we can have any different kinds of edges, right? It can be vertical, non-vertical, or even 45 degrees, or any degrees, those sorts of things. So you can try to extract that. So this could be one exercise for you. What kind of convolutional kernels you can come up with to extract certain kind of features in the image. So lots of people designed lots of filters over the past years, but these days we don't do that anymore. And the key difference, so these are again handcrafted features. That's what we started with. Handcrafted means we discussed earlier, okay, we want to extract edges, we want to do a certain thing, we want to extract a certain kind of features in the image, and we design these kernels, convolutional kernels, so design certain ways of doing things, and we apply that in a deterministic fashion to extract outputs. And the major shift, major things that we do in deep learning now, or convolutional neural networks, is we don't do that anymore. Well, mostly those kind of features. And we train the neural networks, and it will come up with different filters that it needs at different levels. So this is what next week we will talk about, right? So that's what I said. And why do you think these new methods are popular now than handcrafted ones? Sorry? Domain knowledge is not needed. Okay, so because if we want to do the same thing with medical images, we need to know what kind of features we need, lots of these things. We need to know a lot about that. And then we can use, that's one, yeah, that's also a good answer. Anything else? Sorry? With the data, so that will depend on available data also, and the kind of thing you want to do. So deep learning doesn't solve everything. We need to be aware of that. We will need a lot of data and computational power, but it's also about, if you have a well-defined framework, easy to use, where you just feed in data and it comes up with results, instead of thinking for years. Sometimes people took years and years to develop certain methods and come up with these solutions, right? And you have a new problem, and if you have to spend another 2 years to come up with a solution, or features that will be right for it, I think we are lazy, right? We don't want to do that. But more than that, especially in medical imaging, the people are getting interested in this, and they spend years coming up with new features. And then with deep learning, especially, as you said, the results. So these both things are there. The results are getting better quickly when you have more data, and it's getting better than all these handcrafted features. Domain knowledge is not needed. So all these things contribute to these types of methods being unpopular. But it's also true that the accuracy is not that great now for many tasks. I wouldn't say all, but many tasks. But the problem with deep learning, that's what people are trying to solve, is also because when you come up with your own ways of these features, you know what you are doing and what you want to extract and what the algorithm is doing. But with deep learning, it comes up with results, but we are not sure what's going on. Well, partly, right? And this is what we will need to be careful of. And so this is next week. I think Chris and others will talk about these approaches. So Auto-Encoder Pca, that I think we will have to go back again for the code, is also, you can think of in Pca what we were doing, we will have this high dimensional image. We were going to represent it with a small dimensional image. And in Auto-Encoders, which is next week, so it's no more linear here. We will be doing non-linear, but it's still, the idea is same. You want to represent this high dimensional image with a small number of what we call as latent space representation. So the key takeaway from what I presented until now is the importance of having right representation, or learning what representation is good, and also the distances or metrics in this representation, what kind of distances to use, right? So let me try once again. Is Taman there? Taman? Okay, no. I think we can do that in lab. The Pca that I have here, I wanted to show on the slides, but I have uploaded the notebook on the drive also.